Continuing part 2 now of our factoring strategies. So these are just random polynomial expressions we're going to try to factor using the strategies that we know. So in this first example, 6r squared minus 18r minus 60. All right, so the first thing that we have to ask ourselves, is there a greatest common factor that we can pull out? Well, look at the smallest number first. 6 is a factor of 18. It's also a factor of 60. So I'm going to pull out a 6, and I'm going to be left with r squared minus 3r minus 10, right? 6 times negative 3 is negative 18. 6 times negative 10 is negative 60. Okay, so now we have 6 times this trinomial, r squared minus 3r minus 10. And that trinomial has a leading coefficient of 1, right? So we can look at the last term, the negative 10, and ask ourselves, okay, what are factors of negative 10 that add to negative 3? Well, let's see. If I've got two numbers that multiply to give negative 10, one of them has to be negative, right? And I'm thinking negative 5 and positive 2, right? Negative 5 times 2 is negative 10. Negative 5 plus 2 is negative 3, right? And that's what we need in the middle, the negative 3. Okay, so with those two factoring numbers, I'm going to have 6 times the quantity x minus 5 times the quantity x plus 2. Checking this, leave the GCF alone and do the foiling first. So we have 6 times x minus 5 times x plus 2. And foiling, we're going to have x times x is x squared in the middle. X times 2 is 2x. Negative 5 times x is minus 5x. Negative 5 times 2 is minus 10. All right, so we have x squared, and in the middle, 2x minus 5x is minus 3x, and then we have minus 10. All right, now just distribute the 6 through, so we have 6x squared minus 18x minus 60, which is what we started with. Yay! Okay, so let's take a look at this next example. 64x squared minus 80xy plus 25y squared. So with all those big numbers, it's always good to look at whether or not you can factor out a GCF of some sort. So I'm looking at the smallest number, which is 25. That obviously doesn't divide 80 or 64. 5 is a factor of 25. It divides 80 but not 64. So I think we're done, right? And the variables, we don't have a variable that's common to all of the terms. There's no GCF that we can pull out. But the first thing that popped out at me actually is that 64 is a perfect square, as is 25, right? So the first term is a perfect square. We could say it's 8x quantity squared, right? And the last term is also a perfect square, right? 5y quantity squared. So now in the middle, if this is actually a perfect square trinomial, as I'm thinking it is, we're going to have 2 times 8x times 5y, right? Well, 8 times 5 is 40, times 2 is 80, right? And then we have the xy, so minus 80xy. That works, right? Okay, so fully factored, this is going to be 8x minus 5y quantity squared, right? Okay, let's check that. So with 8x minus 5y times 8x minus 5y, when we FOIL this, 8x times 8x is 64x squared. 8x times negative 5y is minus 40xy. Negative 5y times 8x is negative 40xy. And negative 5y times negative 5y is positive 25y squared. Okay, now if we clean up the middle term, negative 40xy minus 40xy is minus 80xy, right? So we're going to have 64x squared minus 80xy plus 25y squared. which is exactly what we started with. Yay. Okay. So notice this is a prime example. Just noticing those perfect squares is such a big deal, right? Because if you don't notice that and you tried to apply the AC method to this, you'd be multiplying 64 by 25 and then trying to find factors of that number that add to negative 80. Yikes. They exist, but it's much easier if you just notice that this is a special form. Okay, now in this next example of x cubed plus 2x squared minus 9x minus 18, the first thing that hits me about this is that it has 4 terms, right? It's not a trinomial, it's not a binomial. It has 4 terms in this expression. So automatically I think, okay, I want to factor by grouping. I'm going to group these, okay? Now, with a negative in the middle like that, with a negative 9x, remember you have to change the sign on the last term when you do the grouping, right? Just to account for that, because you're really factoring a negative 1 out there. Okay, so from that first grouping, x cubed plus 2x squared, I can factor out x squared, right? So I will be left with x, right? X squared times x is x cubed, plus 2, right? X squared times 2 is 2x squared. And then in the next grouping, the 9x plus 18, I can factor out a 9, right? So I'm going to have 9 times the quantity x plus 2, right? That would give us the 9x plus 18 when we distribute it back through, or really with the negative 9x minus 18, right, which was our original expression. Okay, so now x plus 2 is common to both of the terms, right? So I'm going to factor out an x plus 2, and I'll be left with x squared minus 9. Okay, now hold up, because I factored this by grouping successfully, but look at the final product. I have the quantity x plus 2 times the quantity x squared minus 9. What do you notice about that second factor, x squared minus 9? It's the difference of squares, right? So we can keep going here with the difference of squares. With x squared minus 3 squared, we're going to have x plus 3 times x minus 3. Okay, so fully factored, this is the quantity x plus 2 times the quantity x plus 3 times the quantity x minus 3. Let's check this. Now, if you want to do it the hard way, you could multiply x plus 2 times x plus 3. That would give you a trinomial that you'd then need to multiply times the binomial. We could do that, but we know that x plus 3 times x minus 3 is x squared minus 9, right? So if we work it backwards, essentially in the same order backwards as we did forwards, it'll be a little bit easier. But you should get the same thing either way. Okay, so if we're going to FOIL out x plus 2 times x plus 3 times x minus 3, like I said, I'm going to leave x plus 2 alone because you're multiplying, right? You can multiply these in any order that you want. So x plus 3 times x minus 3, we'll do the middle term too. X squared, x times negative 3 is minus 3x. 3 times x is plus 3x. 3 times negative 3 is negative 9, right? Okay, so there is our binomial difference of squares. Negative 3x plus 3x gives us 0 in the middle, right? That's what we wanted. We have x squared minus 9. And then from there, do the FOILing. X times x squared is x cubed, right? X times negative 9 is minus 9x. 2 times x squared is plus 2x squared. And 2 times negative 9 is minus 18. Okay, now is that what we started with? X cubed minus 9x plus 2x squared minus 18. It is. It looks like I reversed the two terms of the minus 9x and the 2x squared, but it's the same statement, right? It's just the same thing with the terms rearranged. So we verified that this indeed does work. So now let's look at this last example, p to the 4th plus p squared. Okay, it's a binomial, but it's not a difference of squares. It looks like the sum of squares to me. Now, before we talk even that far, is there a GCF we could pull out? Well, yes. We can pull out p squared, right? That's what's common there. So when we do that, we'll end up with p squared. P squared times p squared is p to the 4th. p squared plus 1, right? 1 times p squared is p squared. So once we factor out that GCF, we're really looking at that remaining binomial of p squared plus 1. Now, that is not the difference of squares. It's the sum of squares, right? And we can't factor the sum of squares, only the difference of squares, right? I mean, logically, if you think about that as p squared plus 0p plus 1, there are no factors of 1 that can get you to 0 ever, right? One of them has to be positive and one of them has to be negative. But to get a positive 1, when you multiply them, both the signs have to be the same. So no dice. We can't, we're done here. So p squared plus 1 is prime, right? We were able to factor a GCF, but we can't go any further here. This is fully factored. So, and be aware that some of the factoring that you do, you'll find out that it is prime. Maybe there aren't any factors. Not every trinomial is factorable, in fact. But if it is factorable, the techniques that we've used here to get it done will always work.